So what's this talk about? Show of hands, who knows what this is? Okay. It's a low-cost fault injection tool for people to experiment with electromagnetic fault injection. So raise your hand if you've used one of these before. Okay. Raise your hand if you've used one to successfully glitch something to make it do something you want to do. All right. So half the people know. Some people have used one. Some people have used one to do something, which congratulations, because that is incredibly hard. So last year, I spoke at hardwear.io, and I used one to extract firmware from an automotive ECU. It was incredibly hard. My hand is there holding it because that is how I positioned it. There was no XY table or anything like that. It was part of a big chain of attack. And so this talk was kind of born from that work. And I had a bunch of boards made because it's an open source project and it seems to always be out of stock if you try to buy one. And so I had a bunch of boards made. I wanted to see, could I increase the rate of pulses that it can send? So it can basically do one glitch attack per second. And so you heard Jasper talk yesterday about the hundreds of thousands of attacks you need to do to even find anything useful, which is absolutely true. So at one per second, that takes a really long time. The other thing I wanted to do was try to increase the amount of voltage that's fed into the coil. So it's kind of capped at about 250 volts. And there was a number that haunted me that was in my last presentation quite a bit. And so I wanted to see, could I push it beyond that? Could I push the speed up to say like 100 pulse, so 100 times better performance? But I want to do it at a low cost. And so if you haven't heard of me before, I have a YouTube channel, I have a wiki where I publish kind of stuff I've reverse engineered, and a Discord, and I just like to share reverse engineering tools and techniques with people to hopefully like increase the amount of people who are able to perform attacks. I would do a lot of work on smart meters, so if you look at my channel, there's a ton of just hacking smart meters. And then I also started working more and more on automotive stuff. That's kind of more interesting to me now just because they actually try to protect that stuff, where I think smart meters, it's like they do a good job, but like they aren't as actively trying to protect it, I don't think. So I decided I'd put a warning in this presentation, which is kind of a rarity for me. But it is my version of a warning. So I'm just curious, what do you think these three things have in common? What's it? Combustion, okay. Hospital rate, yeah, that's potentially. They're fun, right? They can kill you, so the hospital rate, and you should treat them with respect. So a high voltage supply isn't really much different than that. Treat it with respect. Don't touch the wrong things, do a little reading, treat it as if it's always loaded like a gun is, and you'll probably survive to tell the tale. So this talk I gave last year, kind of to myself, to like a therapist I refer to as the great suffering, because it just really grinded my soul down as I tried to perform this attack using like suboptimal hardware, I would say. And so it was to attack an MPC 5566 chip, which is a pretty widely used automotive chip, to replicate work done by Colin O'Flynn in a paper called Bam Bam, who makes a lot of the tools that I use. Like I said, it's incredibly slow. It can do 1 pulse per second. I was hyper-focused on this number 444, which is a value he mentions in his paper that is the voltage level that he was using when he successfully pulsed the chip. So my brain just got hyper-focused on this. I didn't think about time as a variable in the sense of like the amount of my time that was being consumed versus just spending more money to solve this problem by buying better tools. Now I say I didn't think of it, I did think of it some. So at the beginning of the year after I had completed that project, I started to think like, could I use my own high voltage supply somehow to get past the limitations of the Picoemp, so its ability to charge it up. And so January of that year, laying in bed, kind of scrolling my phone when I should have been asleep, I came across this thing called an electrophoresis power supply. So normally you're looking for high voltage power supplies and they start to be pretty expensive when you want to be able to program and stuff, but this thing was literally $70 shipped to my door and it can go to 3,000 volts. at 400 watts. So it's a pretty, sizable power supply. For reference, a ChipShouter, which is like a super high-end fault injection tool, $5,000, it has a 30-watt power supply inside. So it's a pretty substantial power supply for the price. And it's all things that when you buy them off of eBay, I stuck it in my garage and completely forgot about it. But then I gave the presentation, and it turns out if you say anything about hacking automotive, everyone and their grandma calls you after that to see if you can hack some automotive thing they have. So I chatted with a guy, Alex, who's part of Chippy Partners here, and he said he had an interesting project. This is one of the boards I was using, and me kind of holding my Picoemp over it with just a hand-wound coil that I was using to do fault injection on that chip. And so as part of that work, Alex sent me a ChipShouter to use. So until then, I had never touched one. I'd only seen one in videos. And that thing is, it's amazing when you actually use it. The pulse rate that it can send is crazy. I mean, orders of magnitude more pulses per second. The quality of the pulses is better. It even has signal outputs that you can feed into an oscilloscope. So the top blue trace you're seeing there, right here, is me sending a pulse, so the width of the pulse I want to send. This is using an H-field probe, so it's measuring literally the pulse that's coming out. And then these two signals, the purple one's the voltage, the level, and the green one that kind of bumps out here is the current. And so you can really see that based on the coil I'm using, based on the width of the pulse I'm trying to send, at this point I saturate it and it's no longer effective. So everything you need to define the width of the pulse, to understand all of that, you get immediately right out of this tool. And so it kind of blew my mind, and I almost want to just punch myself in the head at this point, like, why didn't I do this sooner? And then it has this really wide voltage range, 150 to 500 volts, 1 volt at a time, you can really define in. And so that helps when you're doing electromagnetic fault injection. You have a bunch of variables. So you have kind of the position of where this thing is, so you're moving it around, and you have Z height, X and Y. But then you could think of voltage as almost like a fine control. So as I get near somewhere, if the fault's a little too strong, I can lower the voltage, raise it. And so you get all these parameters you can adjust basically to perform a fault. So at this point, I'm like, I can never go back to this thing. This is a pulse that comes out of the Picoemp. It's incredibly long. It's got all this frickin' tail. And I didn't really even measure this until doing the work for this talk. And so then my mind was even more blown, how did I even get this thing to do something compared to what the tool Colin was using when he wrote that paper, which is a ChipShouter. But then my mind is well, why is the ChipShouter so much better? And so the schematic on the right over here, this is the high voltage generation circuit for a ChipShouter. This is the high voltage generation circuit for a Picoemp. So there's significantly more components in one of these than the other. And so I'm like, okay, I guess I could make this frickin' thing, but then I know I want to spend that much time and effort. So that's where this power supply comes in. It's well, what if I just forgo all that and I just pump my own in from somewhere else? And so really the reason that I wanted to do this is there's this massive gap, which is that you can buy a tool for 50 bucks, which is, I use the word tool loosely, it's a toy basically, or you can buy a ChipShouter for $5,000. There's nothing in between in this market. So it's either you can play or you can't play essentially. And there's tools that are higher for sure, like Riskier and Keysight and all these guys, but they're so high that my chart wouldn't even be exponentially, that'd be a logarithmic scale of cost or whatever to include them on this thing. And so what I thought is well, I want to push the Picoemp beyond 250 volts, but how much further can I push it with the hardware that's there? So I looked at the schematic, and so there's this MOSFET, so high voltage generation is being done here. It charges this capacitor. It says it's rated to 630 volts. When I look up the part that they use, 630. The MOSFET itself says it's rated to 650, so I thought, okay, I'll just rip these two components off the board, feed my own power into here, and see what happens. But it turns out that these things, these electrophoresis power supplies, they do a lot of stuff to make sure that the output doesn't get shorted. And when I turned it on there, you kind of heard, so maybe turn up the volume a little bit on these videos, you'll hear this beeping. So it wants to see an output, so it's looking for a resistive load of some amount. And then once that resistive load is there, I'll punch in a voltage. So I'll just do 100 volts. It'll start it. You'll see the voltage climb up right here. This is showing you current. And if I just lightly tap it at all, it goes into this error state. And then you cannot get out of that error state without cycling power to the box. There's no buttons you can press to clear it or anything. So the first hurdle was just how can I even feed this in? So I tried some rudimentary things, like I'll put some little resistors across here and some extra capacitors and try to filter it through a little bit of resistance to charge the other capacitor. And that would work depending on what voltage you set it to. It was kind of every time you had to tune it. So if you set the voltage a little higher, it wouldn't work, and then different values, so it wasn't really a solution. But if you open the box, there just happens to be this board which does that checking. And so if you just connect here instead of here, then it doesn't basically trip out on shorts anymore. And so you do still have to put a little resistor here so it can see a bit of a load, but then you can just alligator clip up here and you're good to go, you're back in it. And so I'm chasing this holy grail number. And I cannot explain how holy of a grail like this was to me. It was so holy that this morning, I'm from Texas, so I woke up and it was a little early or whatever, and I'm like, I gotta go back to sleep because I got this talk, and I shit you not, I roll over, and this is the time that's on the clock. Like, I could not have planned this better for this thing. And I literally grabbed my phone, I was like, this is unbelievable, this fucking number. I take a picture of it, and I was like, and it was kind of blurry, I was like, I need to take a picture, and it literally turned to 4:45. Like, I had the amount of time to cognitively process. So it's like the movie Pi, like that level of obsession in my brain. So the test setup, like how I'm testing this thing as we go forward, I just wanted to show here a little bit. So the way I'm doing it, it might be a little kind of overly complicated or whatever, but I have a function generator. And so I'm just using that to set what kind of pulse rate do I want to try to pump through this thing to see what it can do. The function generator does like a square wave, and it has a pulse mode, but the pulse isn't the kind of pulse I need, which is like a 60 nanosecond wide or something kind of pulse. So I use that to drive a chip whisper. I think pretty much any chip whisper would work. This is just the one I had sitting there. And so that takes my, say, 100 megahertz, and it turns into 100 megahertz, but of very fine pulses that are coming out. That directly controls the pulsing input, the high voltage pulse input, on a Picoemp, which is sitting here. And then this H-field probe is what's going into the oscilloscope as just kind of going to show you the pulse energy that comes out of it. And so this is that view on the oscilloscope here. And so what you're seeing me here do is roll this up, and you can see the pulse that's coming out of it there stays essentially the same, exactly clean the whole time. I'm sitting at 250 volts. I push this a little past 100.47 or whatever, so I can get to exactly 100 on the oscilloscope, because I just want to see it 100 over there. And so I'm like, holy cow, like, I didn't expect that it just hooking high voltage up to it, that it would be that clean. This green line you see up here is the voltage that's being measured right there at the Picoemp itself. So I want to make sure that like it's staying at the 250 volts, and then it obviously dips down as that pulse is hit, but it's able to charge up quick enough from the supply to get back to the 250 volts. And this is just an analog deal I got sitting on top of the power supply. Now I push it to 500 volts at 100 pulses per second, and I got a thermal camera on it here because things are starting to warm up a little bit, but they're still well within, I would say, operating capabilities. It's only 50 degrees C. You can see the pulse is like much better than what a normal Picoemp pulse looks like. And then, I would say if I didn't suffer from mental challenges, this would be considered a win. And this would be in the talk, and I'd be like, this is great, but we all suffer from these same mental challenges, which I feel is summarized here quite well. Come on! I'm dead!
Oh, don't do it, don't do it. Just a little push. Holy shit.
So I didn't have just a little push. I want to do another order of magnitude. So I want to see, could I do 1,000 pulses per second through this, which is starting to approach like the kind of peak level of a chip shouter. So this is me rolling it up just to get it high enough so it'll show 1,000 on the oscilloscope. Same pulse, same everything looking fine. 500 volts at this point at 1,000 pulses per second through a stock Picoemp. Now we're at 140C, and we'll sit at 140C for quite a long time. So it doesn't do a thermal runaway. That's because you'll see I have a tiny fan at this point now pointing at it because it will thermal run away without a fan. But I mean, it can run, and I have the fan set at essentially the slowest speed that I could get it to run just to have some air flowing over. Now mind you, there's no thermal design on this board whatsoever. Like it was designed with safety in mind. There's no vias behind this little MOSFET. There's nothing pulling out to a big plate of copper, none of that. So it's just this little guy sitting there cooking right now. But you can see the timer at the bottom here. I mean, I've been pushing this thing up for 24 minutes basically. Like I went through 200 pulses, 300, 400, 500, just up, seeing if it'll survive, adding the fan. So it's not like it was running for a second or something. It can sustained run it at that rate at this point. But here's the other problem. This is how you change the voltage at this point. So I'm like, I'm gonna give a talk about this. I'm like, well, that is a sucky way to cycle through voltage because a big part of electromagnetic fault injection is changing the voltage as you're doing things. So I thought, okay, like how do I take control of this? There's no USB, there's no USB in 1989, so there's nothing, no interface. They didn't even have a serial interface on this. And I suspect a lot of these are hitting the surplus market because probably newer stuff came out that is computer controlled. And so you just toss these things. So just a little overview of it internally. This essentially is the computer. It's like a Motorola 68,000 and a bunch of stuff that's on here. It comes over this cable right here. It goes into this, and the rest of it's like the high voltage area. It's nice. It already has some optocoupling here for us. And so you send a signal to set the voltage one way, and then coming back the other way is kind of some pulse width modulated signals for voltage and current, and then a few fault signals for whether it's shorted or open or not. And so I thought, okay, I'll use a Pi Pico to replace it because I already have that on the Picoemp. And so I have this wiki. Part of our keynote was you should write your stuff down. So here's me writing it down so everyone else can see it and add to it. I would say a nice thing is like I fed pictures of these boards into Claude, and it did a very good job of just saying, here's everything that's on it, and here's links to data sheets for all those things. So as opposed to looking at all that stuff myself, and like with this board here, it was actually able to infer based on the part numbers that are there, hey, I think this is kind of how the design is working. So it's going from this stage to this stage to this stage. So it's kind of some interesting low-hanging fruit kind of stuff you can do if you feed these things in. And then I documented this header right here, which is how you talk to it to set the voltage and everything else. Now, I got the kind of data by using a Salehi logic analyzer, and I just built this little interposer kind of thing so that I could listen with the logic analyzer at the same time to try to figure out what this was doing as I was setting the voltage. And so this is it set up going to my computer. Now, if you want to measure anything that's plugged into a wall outlet, do not plug your computer into the same wall outlet. And if you do, you will not forget that you did that. And so you won't do it a second time, and you'll have a new MacBook. So I didn't do that, but I'm just saying. And so this is floating, and it's sitting here listening, and I'm capturing these signals. The main signal is how you talk to this digital analog converter that's on the board, which sets the voltage. So you set this line low. This is a clock line. Its signal that it's sending kind of has these odd pulse, like spacing in the clock line as it's doing it, probably because the Motorola chip that's running on there is like, has a certain amount of time and then jumps to something else and jumps back. But you can send these, all 12 bits in a row. Then this is your data line where you're setting a value to this DAC, 4096 different values. To set 3000 volts, it's about like a 0.7 volt per increase of value of the DAC. So then I measured the timing of the clock and the data and everything so that I could describe this and generate a protocol from a Picoemp. This is the hardware. It's just a little interface board to basically connect to those optos, so some pull-ups and some series resistance and stuff that then connects over here. I just used another one of these I had built. Essentially, you could split this in half because I only use this half for the power supply and this half for generating pulses. So basically I had Claude write all the code for the Picoemp. I literally described to it, I need a signal like this. I need you to respect this timing, all this stuff. It created the whole PIO control loop after we went back and forth about stuff. And then I boiled it into an interface so you can read back the voltage just like you would on a chip shouter. You can set the voltage. You build a lookup table, so you do a few measurements yourself at first. You tell it, at this DAC value, so you say I send 100, okay, I saw 66 volts. I send 500, I saw 430 volts. You do a few of those. It builds a table, and then it can interpolate anything after that. You just say I want 35 volts or 300, and it'll set it. So that's like the initial configuration that you do. This actually I forgot to set public, so I'll do it right after I'm done with my talk, but that's where you'll go to get this code. It's up there. And so then a breakdown of cost. So the Picoemp is $50. The power supply, I said 150 because I imagine it'll go up a little bit after this. So I doubled the value there. And then generous on the wires, resistors, capacitors, and a fan. If you're building this, you probably have all that crap already, honestly. And then if you want to put it on a CNC platform to move it around, which it's a little less hand-holdable at this point safely, so probably a couple $100 for that would be good. But the thing itself, you can do for under $250. Now, I wanted to say it's not, in my mind, it's not a chip shouter replacement, and I'll show you some reasons why not. It's probably a good second rig for a number of things, but the chip shouter has better pulse control, repeatability, a much better thermal design, all this. So to me, it's if you're doing this for a living, you have a chip shouter, and then maybe you have something else like this, which gives you a second rig to do some serious high frequency pulse rate kind of stuff, but you have your primary one for when you're really trying to hunt with a chip shouter. But for like a hobbyist, for somebody playing in their room, this is like epic. Compared to 1 pulse a second. Really, you can do voltage control on Picoemp because I did it and I wrote the code to do it, but it's kind of rudimentary, and then the pulse rate's super slow. So the funny thing is, the more I compared performance for this talk, the more I was like, God damn, the chip shouter is just a really good tool. Like, my respect level just kept going up for that thing. At first I thought, like, I'm just gonna replace it, $250, and yeah, not quite. So just to make sure, same page. So setting the pulse rate with this, defining the width of the glitch with this, using the H-field probe to measure the energy that's coming out, and then I go through some attenuators here into my oscilloscope so I don't, pulse too big when I'm going in there. So here's a Picoemp, 1 pulse per second, kind of a crazy pulse. Here's the supercharged version, 1,000 pulses per second, a much cleaner pulse coming out of it. And you can see what I'm trying to send here is about 60 to 80 nanosecond wide pulse, which is pretty close to the narrowest you can get with the triggering in the Picoemp, its trigger circuit that it's using. Chip shouter has a much better trigger circuit to drive the MOSFET. And then this is on a chip shouter. So you see it's wider here. It's just because my width is set wider on the scope. This is, as clean as it gets. This ringing is likely me, not anything to do with it. It's just my wiring and everything. But you can push that thing beyond 5,000 pulses a second without even starting to cool it. So I wasn't even pumping air through it like you can do to cool it. So that tool is crazy. That's not the craziest thing though, because at 1,000 pulses per second, you're saying, I'm gonna do my entire glitch setup, get a trigger, do something, and in 1 millisecond, start all over again and do another glitch. That's already crazy fast. So the real power isn't in that repeatability, it's in sending multiple pulses. So when you have to do a few glitches as part of a chain to exploit something. And so the Picoemp is like, don't forget about it. That is not even, you're not even thinking about that. With this, I can do it about every 20 microseconds where I send the same width of a pulse that I want, and I get about the same energy out. You can see the voltage starts to kind of ladder down a little bit because my capacitor bank is kind of falling down. And there's tricks you can do to say, like, I want a 60 nanosecond pulse here, and then here I want like 150 nanosecond pulse, but really what comes out is another 60 because of the falling of the capacitance. But without any tricks, just what can I do, asking the same one. And then this one's 150 nanoseconds. So like this is 20,000 nanoseconds to 150. So the ChipShouter is a crazy tool when you have to do multiple in a chain. But to me, I don't need all the stuff that's in a ChipShouter. Like, to me, the ultimate platform would be just give me the really good driver, some capacitors, a FET, and let me feed in this other stuff. And so the assumptions I make is that you're somebody like me. You probably already have a chip whisperer, some kind of fault injection tool. You already have power supplies and this stuff. You just kind of need this raw hardware to feed it all into. And so this is the MOSFET driver circuit that's used to drive the high voltage pulse on the ChipShouter. In comparison, on a Picoemp, it's just like one little MOSFET and a transformer coil. So this thing, when you look up the data sheet on this part, and even Colin here says like tuning this is part of the magic. Like, so there's a lot of work for sure that goes into this, but this is the magic of literally turning this MOSFET on hard, turning it off quickly, and getting a super clean pulse out of there. And some kind of EMP reservoirs on this board because my power supply is kind of further away. So I'm running it through some kind of cabling over here. So I probably need some intermediary kind of pool of capacitance to hold my value that then goes to my capacitor that's going to be doing the pulsing. And oscilloscope monitoring, like you see, these are the outputs you can get right off of it. That is like the coolest crap ever. And when you look at the schematic, I mean, it's not that complicated to add that. Like, these are just some resistors and things so that you can feed it out. But to be able to get this level of output, this is really what takes you from like you're guessing what you're doing to you're really defining and you're understanding and you're wrapping your own coils and you're profiling what their capabilities are and all these things. And there's some kind of heat dissipation and monitoring is helpful so you don't blow up your system. And if you're doing stuff like this, get yourself a thermal camera if you don't have one. Like, this crap is cheap as hell nowadays as a tool, and it's super useful for looking at anything just to see what's going on it. What I don't need is like some kind of a brain that's in it. Like, I don't need any kind of digital controller interface, I just feel like it adds a lot of cost and complexity to put it inside that device. And maybe some safety, that adds a lot of cost too, like what they must have to do to sell a ChipShouter and all the safety work. I kind of feel like just give me the raw hacker tool and don't worry about all that crap. And so this literally was last night screenshotted, 75 bucks. And there's a lot of them on there sitting there at this price. This is the first time I gave this talk, other than a couple people I told before this, like, if you want to buy one of these, they're literally still on eBay right now, and a few weeks from now they won't be on eBay. The thing to look for is what I found is like an electrophoresis power supply. This one specifically is a 3000 XI, which means it can go up to 3000 volts. So you do have to look at that model number to make sure what you're buying gets up to a high enough voltage. I also have some other different brands that I've bought, just I thought it'd be interesting to see what's in them, and they're pretty cheap. Like, even just as a programmable high voltage power supply now, you can literally set anything from 20 to 3000 volts for under $100. That's pretty handy for all kinds of stuff. And they seem to have a similar design just by the nature of what it is. There's a high voltage section, there's some kind of optocoupling, and then there's a computer. And so you just jack in the middle in that optocoupling piece. And so the reason I wanted to present this and that I did this work is that I think a lot of what separates us or people that are in a room from some highly funded academic or nation state actor is a lot of times tooling. And if you get access to better tooling, you can do a lot more interesting things. And so that's what drives me. And so thanks for your time.